So we're going to pick up on lesson 11, which practice a few questions of using our units of concentration. So first two are going to be using our dilution formula. So just to remind you, it's M1V1 M2V2, which is, this is the molarity and the volume of one solution, the molarity and the volume of a second solution. Sometimes it's also shown as C1V1 C2V2, which just is concentration. So you can use the dilution formula for any units of concentration that we have, but because molarity tends to be the one that we see in chemistry, we have the M1V1 M2V2. So the first question says, if I have a certain volume of a certain molar solution and it's diluted to a molarity of this, what is the volume of the resulting solution? If I can label it as I go and figure out which pair go together, then it's a matter of just plugging them in, making sure that the units match. So I'm given units of molarity, I'm given units of liters, so my final answer is going to come out in liters, which this doesn't specify I need any other units. So I'm going to plug these values in. And I'm going to multiply the values on the left and divide by the molarity on either side. And that's going to give me a volume of 0.782 liters. I have 3 sig figs here, so my final answer is going to have 3 sig figs as well. So let's practice another one. What volume of this molar solution can be diluted to prepare this volume of this concentration? Again, my units are both in molarity. These volume units are in milliliters. My question doesn't specifically say I need to have any other units other than what I'm given. So I'm going to report my answer in milliliters because it's what I'm given to start off with. So I'm going to plug in my values. I'm going to multiply the values on the right, divide by the 0.33 onto either side. It's going to give me a volume of 1.9 milliliters because I have 2 sig figs in all of my answers, all of my initial numbers, so I'm only going to report 2 sig figs. So now let's look at the trend. The trend is that when we have a higher molarity, the volume is going to be smaller. When we have a lower molarity, the volume is going to be larger. Okay, so as the molarity goes up, the volume will usually go down. In this case, the smaller molarity, the larger the volume. The larger the molarity, the smaller the volume. Okay, so when we're diluting a solution, we should expect the concentration will go down, but the volume will be going up because we're diluting it. We're adding more solvent and we're holding the amount of solute the same. What mass percent of a 4% solution of sodium hydroxide contains this amount of sodium hydroxide? So this is a mass percent problem. So this is going to be mass of solute divided by mass of solution times 100%. So I'm going to plug in all my values that I'm given. My X is my mass of my solution. That's what I don't know. So multiply by 100%. So if I want to get rid of the percent, I can simply convert the 4% to its decimal form. The X is going to multiply to both sides. When I do that, I'm going to get so now I'm going to divide out that to both sides, and I get a value of 375 grams of solution. I have 2 sig figs and 3 sig figs, so if I'm going to round this up, it's going to be 380 grams of solution according to sig figs. The next question says, what mass of HCl is contained in a certain volume of aqueous HCl that has a density of this and contains this percent by mass? So the first thing I need to do is I need to determine, so I have, I'm going to use the same formula. So I have 37.21%. I want to know what the mass of HCl is. That's my unknown. But my mass of my solution, I only have a volume. And what I need down here is mass. So I don't have the value I need right now. But if I have the volume and I have the density, I technically can convert for mass using our density formula or the train track method, and that will allow me to plug in the mass solution. So to do that, I'm going to start with my volume, 45 milliliters. 1 milliliter is equal to 1 cubic centimeter. We learned that in one of our chapter 1 lessons. And I'm going to plug in the density here, which is 1.19 grams for every 1 cubic centimeter, which is going to give me a mass of 53.55 grams of solution. So now I have the bottom value I need. Just like the last problem, I'm going to get rid of the 100% by moving the 37% into its decimal form. When I do this, I can see I need to multiply 53.55 to both sides, and this is going to give me an x value of 20 grams of HCl. I have 3 sig figs in my answer, so I need 3 sig figs. I have 3 sig figs in my initial numbers. I need 3 sig figs in my final answer, which gives me 20.0. Last problem is a throat spray is 1.4% mass phenol, which is this compound in water, so it's a solution. If the solution has a density of this value, calculate the molarity of the solution. So if I have 1.4 grams of phenol, and I'm going to assume 100 grams because I could, just like we did empirical formula where we took the percents and turned them into grams, I can, because it's 100%, I can assume grams and put them into percents. The other 98.6% or grams is going to be water. So what this means is if I have 1.4 grams of phenol, it's going to be in 100 grams of solution because these two together are going to equal 100%. Then I'm going to use the density because the density is of the solution. For every 1 milliliter, because that's the units I'm given. And I'm going to convert that to 1,000 milliliters for every 1 liter. So now the units I'm going to get are going to be in grams will cancel out, milliliters will cancel out. It's going to leave me grams of phenol to 1 liter of solution. And that's going to be 13.9 grams of phenol for every 1 liter of solution. So to get to molarity, which is moles per liter, I need to convert phenol from grams of phenol to moles of phenol. And I'm going to do that using the molar mass, which is why I needed to know the formula. The formula or molecular mass for phenol is 94. So when I take 13.9 and divide it by 94, I'm going to get a value of 0.148 molar because the grams will cancel out, leaving me with moles of phenol per liter of solution.